Okay, students, welcome to video class 7. And the topic again is modeling of physical systems, part 4. And this is the last session of this topic. And in this topic, in this session, we will be doing some problems related to mechanical systems. Okay, now let's move on straight away to the problem. Here is a question number 1 for you. Now, I will explain the question. So you have again a mass damper spring. This is a spring. Okay, so this one is like this. Okay, so this one is a spring with the spring constant K, and this is a mass. Okay, so the mass attached to it with the mass M, and this B is actually, so this mass is on a surface. So this is showing the surface, and this surface offers a frictional force, and that is represented. That's the frictional force coefficient is represented by the letter B. Okay. Now what happens is this force. Now, the mass on the mass, a force is applied. So when f of t is applied on the mass m, that will result in a displacement x of t. Okay, now the first thing that you need to find out, that is, the question is okay, let's see the question. Find the transfer function of the mechanical system, and the second part is to obtain the block diagram representation. The main aim of this, the actually what I meant is, you must understand this. So this is usually asked in the exam, but obtaining the block diagram is not regularly, not seen in your exams. It's not asked in the exam, but it's nice to understand how to obtain the block diagram. And the same question we have studied in the electrical system as well. There also I said it is the most important thing is to find out the transfer function, and the purpose of this is, when we start with block diagram detection technique, we will again make use of this. So the transfer function which we find right now, we'll have to get the answer as well as for the block diagram detection technique. Okay, that's the objective of this question, the second question. So the primary question is question number 1, which is you are to find out the transfer function. Now, in order to find the transfer function, first of all, you need to identify the input and the output. The input is f of t, while the output is x of t, right? So we know that the transfer function of the system is equal to x of s. That is the Laplace transform of the output to the Laplace transform of the input, that is f of s, with the initial condition to 0. Now, in order to get this, we need to have the equation corresponding to this. Okay. Now, there is actually a sequence of there is a sequence of steps that has to be followed. The first thing is you must have a free body diagram. Okay, this is the first thing, the first step, free body diagram. Now, the free body diagram is is always drawn with respect to mass. Suppose in this system you have only one mass. Now, in the next example, we'll be seeing more than one masses in a mechanical system. There I will be explaining how to draw the free diagram in that. Now, in this case, so the free body diagram is always drawn for the masses or the mass in that mechanical system. In this mechanical system, you have only one mass. Okay. Now, the free body diagram actually shows the various forces that are acting on that body or on that mass. That's the meaning of this free body diagram. So here you have a mass, and on the mass you have an external force, that is your input. So the external force has to be shown by an arrow moving away from the mass. Okay, and all other forces which are acting onto the, because of this external force, some forces are acting on the body, that has to be shown into the inward, right? So this body, we know that this body moves with this x of t, right? So free, in the free body diagram, the only the forces are to be shown, the various forces that are acting on this mass. So since it is an external force, we'll have to see, show it by an arrow pointing away from the body, and all other forces other than the external forces are to be shown into the towards the body. Now what are the other forces? We can see that there is a force associated with the spring, so let us call that as F. Yes, right. Fs, or the force related to spring, and another force is there, that is the force related to what? Force related uh, related to the spring, or since it is the spring constant, let us call it as Fk, while this is Fb. Okay, right? Now these are the forces that are acting on this mass, right? And another force is a force due to this mass, and let us call that as Fm. Okay, now what must be this, as per Newton's second law, what you need to draw is this. You know that the applied force is equal to the opposing forces, so that is actually, it is equal to Fm plus Fb plus Fk, right? Now what is this Fb? Now, what is this Fm? We know that this Fm, which we have dealt in the previous session. What is this Fm? Fm is, if x of t is the displacement, this is m into d square x by dt square, right? So that is mass into acceleration. Now, what is Fb? That is the force due to the the damper, dashpot damper will be b times, b is the coefficient of damping, so this is dx by dt, while what about Fk? That is the force due to the spring constant is k into x, right? So you can write this equation as this f of t is equal to what? F of t is equal to m into d square x by dt square plus b into dx by dt plus k into x, right? So you got one equation. So generally you can say that it is just similar to when you write node equation and mesh equation in an electrical network. Suppose you have three meshes in a network. You can see that you have three equations. So similarly, to be, I mean, it's a general statement. It need not be always true, but generally, if you have one mass, then you can expect one equation. If you have two mass, then you can expect two equations corresponding to that. Now, from this equation, we will be able to find out. Our objective is to some way or other to find out this x of s to f of s. Now, what's the next step? The next step is to apply the Laplace transform throughout one, right? Throughout one. So we'll get this as f of s is equal to m into s square into x of s. The rest we ignore because the initial condition is 0. M into s into x of s plus k into x of s. So you're going to get the same expression as we learned in the previous video. So this will be x of s into ms square plus bs plus k, right? So bs plus k, or what about x of s by f of s? X of s by f of s, which is the transfer function, that is given by 1 by ms square plus bs plus k. Okay, so this is your transfer function. So that's the first the answer to the first question, that is to find the transfer function. Okay. So the following steps are to be noted. First one, we draw the free body diagram corresponding to each mass, and then we write equation corresponding to that mass by applying the Newton's second law, and then on that equation we will be applying the Laplace transform, take the wanted ratio so as to get the transfer function. Okay, now coming to the second question, we are to obtain the block diagram representation of this. So I told you this is not as important as this, but anyway, it's nice to know how to obtain the block diagram from this. Okay. Okay, now how to draw the block diagram. So mark this equation as 2. Now from 2, okay, from 2, that's what I'm going to do is, I'm going to find out the expression for m into s square into x of s from this equation, so that you can bring these two terms to this side, so that that equation becomes m s square into x of s equals f of s minus b s into x of s minus k into x of s. Okay, now from this you can obtain the output like this. X of s will be f of s divided by m into s square minus b into s into x of s by ms square, okay, minus k by ms square into x of s. Now this s and s you will get cancelled, so that this expression becomes f of s by ms square minus b into x of s by ms minus k by ms square into x of s. Okay, now coming to this expression, you can see that these two terms are having the same denominator. Okay, now let's see how to relate this. This is actually the expression of x of s, which is your output. So here is your x of s. Okay, this is how I have explained in the previous time when we did the electrical system. So this is your f of s. So if you have any doubts, you may just refer that and then come back to this. So we know that this is to be 1 by ms square, right? But there is a term called as 1 by ms as well, right? Now what happen if I have a block something like this, 1 by s, 1 by s. So whatever comes here, say let this signal be, say some x or y, say small letter w, right? W, this will be w by s. We know that. So when I take this, so this, what does this suggest? Minus sign suggests that I am taking the output, taking the feedback. This represents a negative feedback. Now I am actually going to compare with this f of s by 1 by ms square. Okay, now here I have a summa. Okay, here I am putting a negative sign and with the block k. Okay, now as per this diagram you are getting only k by s, right? But I want what? I want ms square. So what you need to have is one more block. Suppose imagine that you have one more block with 1 by ms, right? So what will happen is, if these are connected together, say I'm just forgetting this for the meantime, I'm just considering the terms which are having the same denominator. So now look, just look at this expression. What about this? This is f of s. F of s into 1 by s into 1 by s becomes f of s by ms square, right? Minus k by, what about this? K by what? X of s. K by, right, k by Now this k, now the k also goes like this, right? So this is what comes over here. This will be f of s minus k. F of s minus k into 1 by ms will be f of s minus k divided by ms. When it comes here, you can see that this term will be f of s minus k divided by ms square. So that is actually this term, right? These two terms. Now, this is not actually your x of s. X of s, you have one more term with b. Now, you know that if you have, and this is also feedback. That means there is one more feedback. Say, you can have a feedback something like this, right? See, the signal that comes over here, say C is the signal, this will be C by ms. So any signal coming at this point will get multiplied by 1 by ms, and it has to be fed back in the negative feedback. Say suppose, assuming that, so this will be minus, but with a block of b, right? Now what happens? I will explain this. So what will be the signal that comes over here? If this is x of s, what will be this? The particular signal is multiplied by 1 by s, right? So then it becomes x of s. That means this is also x of s multiplied by s, right? Now what will happen when it goes through this? S into x of s divided by 1 by s gives you x of s. So the signal over here is x into x of s. So what it takes is b into s into x of s, right? And b into s into x of s, right, divided by, it goes over through this block and comes over here, right? So the final output will be bs by ms square, and this s and s get cancelled, so it will be, you'll be getting this. So this is actually the block diagram representation of this simple mechanical system. Okay, now as I told you again, that this is not that much important, but anyway, when we study block reduction technique, we will come to this example as well and prove that the transfer function is the same as this. Okay, now the third part of the question, so I've added one more question to this. Draw the mechanical circuit of this diagram. So you can have a mechanical circuit, and that sounds similar to electrical circuit. Okay, so this we follow always a forced current analogy type, that will be followed here. Now, while drawing the mechanical circuit, you need to understand. So, what are the fixed points over here in the mechanical system that's shown? That means you can see that a spring and the damper, they are fixed, and one of this side of the mass is also fixed, right? Now, there is only one displacement. So this is a very important thing. So first of all, when you draw the mechanical circuit, this is very important. This is usually asked in the question in the exam. So the mechanical circuit, when we do a mechanical circuit, we employ knots. So how many knots you will be having? The knots will be equal to the number of displacement. So in this diagram, you have only one displacement. That means you have one knot, and the fixed knots, the fixed points are called as reference knot. So you can have a reference node as well. Now in between this, we will be drawing. Now in the reference node, what you can see that this is a fixed point, this is also a fixed point, and one of the side of the mass will also be considered as fixed. So the fixed points will be considered as the reference node. Now the first thing, let us start with this side. That is, f of t is actually the input that you apply. So between this node, it's always, so you need to draw like this. Between this node, you have an f of t, that is you have an f of t, that is f of t between these two knots, then so this is your, this has to be marked as your x of t, right? Now common to this, that is there is a fixed point as well as a, now the fixed point is the reference node, and the movable point, that is the x of t. Here you have only one x of t, so the x of t is being experienced by this mass, by this damper, by the spring. So that means all this comes in parallel to this, right? This is x of t. X of t is common for both mass, then you have what? You have the mass damper system, then you have the spring. Okay, so we will call this as mass, this as B, and this one as K, right? Okay, right? That's it. So this is the knot. Now you can write the knot equation. That is, what is knot equation? The incoming is actually equal to the outgoing. So you can write like this: incoming f of t is equal to, then what is outgoing? Outgoing will be m into d square x of t by dt square plus m into dx of t by dt plus k into x of t. Okay, so this is how we frame up the equation. So from this, this is actually the mechanical circuit of the system that is shown in the figure. Okay, so you'll be understanding it when we do one more problem of this type. Okay, so you have a next problem is you have a mechanical system shown. You are asked to find the transfer function and draw the mechanical circuit. Now here in this problem, compared to the first problem, no externally applied force is shown. This y1 and y2 are the two displacements occurring at two knots. So I told you earlier that the knots in the circuit, when you draw the circuit, the knots represents different displacement. Now you have two displacement, meaning you will be having two knots. Okay, so it will be nice if you start with the equivalent mechanical system, so it will be able to, you'll be able to write down the equation, right? Now now let's start with the, as I told you, free body diagram. The free body diagram is always related to the mass. Now how many forces are associated with that? No input force is shown in the circuit, so you cannot have any, but only two force. One force is due to a force due to K1, right? Then another force is due to K2, that is the spring, while another force is due to FB, right? So these are the three forces, and the next one is due to this displacement y2 of t, another force is associated with this mass. So you can write that the applied force is actually shown as there is no applied force, right? So no applied force is there. So you can write all those things as equal to, say, as equal to 0, right? No. Right. So these are the, this is the free body diagram of this. Now let's try to do the problem. Now when you compare this this mass with respect to this mass, if you write the equation, what is Fm? Fm is actually equal to d square y2 of t by dt square, right? Okay, now what about the mass due to this fk2? Fk2 is actually equal to k2 times, what is the displacement associated with this y2, right? y2 of t. Now what about this b into dy2 of t by dt, right? So this is it, m into, so this is m into d square y of t by dt square plus k into y2, k2 into y2 of t plus b into y, d by 2 of t by dt. Now how many components? 3 components, but in the diagram it's showing again fk2. So there must be another force related to this k1, right? Fk1. So what is this? This is actually, so when you write equation with respect to this spring is under the action of two displacements. One is Fy1 and Y2. But you are writing with respect to this mass, so you can write this equation as K1 into Y2 minus Y1 of t, right? This is equal to 0, right? Or now from this equation, what you want to find out is what is the transfer function of this. So you will have to assume that this is a displacement, the initial the displacement y1 of t, and that might have resulted in y2 of t. So the possible transfer function is just to find out y2 of s to y1 of s. Okay, y2 of s by. Now, what's the next step? That is to apply Laplace transforms. Hope you understood why I took y2 minus y1, because this is actually similar to NOT equation. Now, when you have a NOT voltages like v2 and v1, when we write equation corresponding to this NOT, we will take this as v2 minus v1. Similarly, you take the displacement like this, y2 minus y1. Okay, so this is equal to 0. Why 0? There is no applied force is shown. For by somehow a displacement occurred, and that displacement resulted in another displacement called as y2 of t. So we are just finding out y2 of s and y1 of s. So how will you find out the Laplace transform? This is m into s square into y of s. No need to write the rest. Plus k2 into y2 of s. This is y2 of s. This is y2 of s plus b into y2 of s plus k1 into y2 of s minus k1 into y1 of s, right, is equal to 0. Now all these terms you have y2 and there is only one y1 of s. So you can bring that y1 of s there. So this becomes k into y1 of s is equal to ms square into y2 of s plus k2 into y2 of s plus b into y2 of s plus k into y2 of s, right? Now you can take y2 of s outside, so that this becomes y2 of s is equal to into ms square plus k2 y2 k2 plus b plus, what about this? This is k1, right? Plus k1, right? So that means what you want to get is, this is k times, this is k1 y1, right? K1 y1 of s. Now what you want to get is 1 pi. Okay, so you want to get this as y2 of s by what you need is y2 of s by y1 of s. So what is the transfer function defined? This is defined as y2 of s by y1 of s. This will be k1 divided by ms square plus, I'm bringing these together, so that is k2 plus k1, right? K2 plus k1 plus b. Now I think there is b into s into y2 of s, so that will be, yes, there is a mistake. This is s, so this is b into s. Okay, so this is bs. So the transfer function will be like this. You can write this as a quadratic expression like this, ms square plus, in its order, this will be bs plus the constant, that is the sum of the spring constant. Okay, so this is your transfer function, right? Now how to draw the mechanical circuit of this? Now when you draw the mechanical circuit, this is the point, this is actually the input point, right? That is the node. There are two nodes because two displacement. So I will start with this node A, and this node A is open. because nothing is said about the input. So you have a reference point and the node starts with A. Now in between this node A and this node you have a K1. So you can represent that as K1 as a series this thing. So this becomes the node Y2. So you can call this as Y2 node, right? So this will be Y1 node, Y1 node and Y2 node. Now this Y2, now coming to this Y2 node, this Y2, this displacement is experienced by mass, by dashpot damper, by the spring. So, and one of those things will be assumed. Now look at this damper and the spring is the one of the ends is located at the fixed point, and as I told you earlier, that in the case of mass, one of the side of the mass will also be assumed to be fixed. So that means one of the side, the fixed always refers to the reference node. So you can have a parallel connection of this. So you can have something like this. This is M1, then you have a damper, this is B, and you have a K2, that is the spring, you have a K2. Okay, so this is actually the mechanical circuit of this system. Okay, hope you understood this. Okay, now coming to the third question, question number 3, which is quite different from what we did previously. So let's have a look at the question. You are asked to find out the transfer function of this system, and after that you are required to draw the mechanical circuit. Now coming to this system actually has two masses, and that is named as M1 and M2, and this M1 and M2 has got 4 other components, and you can identify that as 2 dampers and 2 spring, and the damping coefficient is given as B1 and B2, while the spring constants are K1 and K2. Okay, so B1 and B1 K1 are in between M1 and M2, while B2 and K2 is exclusively for mass M2. Now you have the applied force that is applied on mass M1. So that's your applied force, which is given by F of t. Now because of the application of this force, this M1 actually moves with the displacement given by Y1 of t. And you have another displacement due to M2 that is also given as Y2 of t. Now, as in the question, the transfer function, you are supposed to find out Y1 of s divided by F of s, because this Y1 of t is considered to be the output in this question. Now, this question can also be asked in another format, that is to find out Y2 of s by F of s. Still, it is a transfer function in a different angle. Okay. Now the first step of approaching this problem is to draw the free body diagram. Now, as I told you earlier, the free body diagram depends on the number of masses. So in this system, you have 2 masses, M1 and M2. That means you have 2 free body diagrams corresponding to mass 1 and mass 2, M1 and M2. Now coming to M1. Now we know that from this figure it is very clear that the force is applied on the M1, or this is the external force. All the other forces are generated internal to the system, but this force, that is the F of t, is actually an external force. So the M1, when you draw the free body diagram for M1, you have an F of t with an arrow which is pointing away from the mass. Now, what are the other forces that is associated with M1? Now, as it is mass, you have an inherent force due to the mass, and let us call that as Fm1, right? So this is Fm1, meaning this is the force due to mass M1, right? and that depends on what? Depends on the acceleration due to this displacement y1 of t. We'll come to that later. Now, then what about the b1? So b1 is actually a damping force, okay, and that uh, b1 is actually a damping force, and let's call this as fb1, which denotes the force due to this what we call this as damper, dashpot damper. And you have one more spring, and there will be a force due to that spring, okay, or that is represented by fk1. So how many forces are, that this mass is m1 is associated with? You have four forces. One is an external force which is applied. The other three forces are the forces corresponding to mass 1 m1. Then you have the force due to the damper, the dashpot damper connected to it, and again you have a force due to the spring connected to mass 1. Okay, now coming to m2. M2 is quite different. That is, the number one thing is that no external force is applied to m2. So there is no need of any arrow showing externally or going away from m2, because there is no external force. Now let's see what are the various forces that m2 is concerned with. Now coming to this m2 is connected to k1 as well as b1. So there must be a force due to fk1, and that is internal. Sorry, this is internal. It has to be shown internal. And in another force called as fb1. Okay, so these are the forces due to these two springs, because this spring and this damper are connected to both mass 1 and mass 2. Now you have two more forces, like in the form fb2 and fk2, right? So this fb2 is exclusively for m2, while fk2 is exclusively for this m2. Now one more force is there, that is the force due to m2, and let us call that as fm2. Now look at the difference between the free body diagram of these two masses. The first mass is having only four forces. Among that, one is the external force. Now what you are going to do is you are going to equate this external force to the opposing forces. F of t is equal to this thing, right? Now coming to this, there is no external force, so the external force is equal to 0. That means the sum of all these forces is equal to 0. How many forces are there? 1, 2, 3, 4 and 5 forces. And when you take the sum of those 5 forces, and that's equal to 0. Okay, so this is the thread of finding out the equation corresponding to this system. Okay, now let's see how to frame up equations. So once after you have drawn the free body diagram, from the free body diagram you got an idea regarding the forces, the various forces that's acting on each mass, and based on masses you will have equations. As I told you earlier, depending if you have two meshes in an electric circuit, you will have two equations. So similarly, if you have two masses in a mechanical system, you will be having two equations. Okay, now considering the free body diagram of M1. When you consider the free body diagram of M1, you should look for the external force. The only external force is given as F of t. F of t is equal to, what is force M1? Force M1 is the force due to the mass M1. You can say that is M1 into, it is actually, what is the displacement associated with M1, which is Y1, and it will be d square Y1 by dt square. Why this is? Because the force associated with the mass is actually mass into acceleration. So this is d square y1 of t by dt square. Plus, what about fb1? Fb1 is actually equal to the b1, right? b1 is a damping coefficient into dy by dt, right? Then finally you have what? You have fk1. What is that? Fk1 is actually k1 into y1. Sorry, this is dy1, this is dy1 of t. Okay, you can put it like this: y1 of t, k1 into y1 of t. Now what is the next step? Now from the free body diagram, so from the free body diagram of M2, what is this? What is the left hand side? Left hand side always denotes the external force. There is no external force from the diagram, so that this is equal to 0. Now this 0 is to be equated to the sum of all these things. So that is, say, coming to FB1. Let's consider this FK1 and FB1. So what is the speciality of FK1 and FB1? Because this K1 and KB1 are both common to M1 and M2. So when you write equation for that, it will be, okay, okay. So now the next objective is to frame up equation based on free body diagram. So consider the free body diagram of M1. Free body diagram of M1. So you must be very careful in writing the equation. Now considering free body diagram F1, of M1, you can see that there is only one external force. So the external force, let us call that as the LHS, left hand side. So that F of t is equal to the sum of all other opposing forces, that is Fm1, it is equal to Fm1 plus Fb1 plus Fk1. Okay, now this Fm1 is actually, when you look at the picture, you can see that this F, the force acting on M1 is only due to what? Due to this Y2. This M1 displaces by Y1. That means the force associated with that is related to only Y1. So we know that the force associated with the mass is mass into acceleration. If you know the displacement, the acceleration is d square y by d square y1 of t by dt square. So this is d square y1 of t by dt square. Now coming to FB1. Now there is a speciality in FB1. Now this B1 is connected to both M1 and M2. That means this B1 experiences a displacement Y1 as well as Y2. So there must be a net displacement. Now since you're writing equation for M1, the net displacement will be the displacement due to M1 minus the displacement due to M2. Now what is the displacement? It is Y1 of t minus Y2 of t. So this will be B1 into the derivative of what? D by dt of Y1 of t minus Y2 of t, right? Then next one is, what about the next? Next is Fk1. Again you have a spring constant which is also connected on either, on the two masses, between two masses M1 and M2. That means this gets affected by these two displacements. So you know that it is the spring force is proportional to the displacement, or you can say the difference in the displacement. So that will be K1 into Y1 of t minus Y2 of t, right? Okay, now that's the first equation. Now coming to the free body diagram of, okay, coming to the free body diagram of M2. What is the free body diagram? Now what is the external force? External force is 0. 0 is equal to Fk1 plus Fb1 plus Fb2 plus Fk2, right? Now 0 is equal to, what is Fk1? K1, now coming to this K1, as I told you before, the explanation is the same. Now it's in between M2 and M1, but we are writing equation with respect to M2. That means the difference is Y2 minus Y1. But you want, since it is Fk1, it is corresponding to the spring constant, it will be K1 times Y1 of t, Y2 of t minus Y1 of t, right? Then what about Fb1? Fb1 is the force due to the dampers proportional to the derivative of the displacement. Now here you have the displacement difference, that is Y2 minus Y1. So it will be dy dt of Y2 of t minus Y1 of t, right? Then finally, coming to the, then you have one more FB2, FB1, FB2, F, and okay, you have an FM2, right? Now, then you have an FB2. What about FB2? FB2 is having only displacement. It's only affected by this y2 of t. That means this FB2 is represented, this, the force due to this is actually given by, so this is B1 into the derivative, right? Now what is FB2? So this is B2 into d by dt of y2 of t. Okay, hope you understood this, because this B2 is proportional only to the displacement. Now finally, then you have K2. K2 is related to y2 of t. So this is K2 into, this is K2 into what? Y2 of t, right? Now finally you have FM2. What is FM2? FM2 depends on the displacement, on the second derivative of the displacement of this. So this will be m2 into d square y of t, y2 of t square by dt square. Okay. Now look at this. You have two equations, 1 and 2. Okay. Now what's the next step? By applying KVL to this. Now applying, it's not KVL, applying Laplace transform to equation 1. So let's see what is that. Equation 1. Okay, this is the equation, right? So applying Laplace transform to this equation, that is d square y of t by dt square. What is that? That will be s square into y1 of s plus, then you have here you have m1, right? So m1 into s square y1 of s plus, next is b1 into s into y1 of s minus y2 of s, right? Then finally you have a plus k1 into y1 of s minus y2 of s is equal to what? Equal to f of t, f of s, equal to f of s. So call this as equation 3. Now similarly you can apply Laplace transform to 2. That is, when you apply Laplace transform to 2, you can write this as 0 is equal to k1 into y1 of s minus y2 of s plus b1 into s into, right? S into y2 of s minus y1 of s plus b2 into y2 of s plus k2 into y2 of s plus m2 into y2 of s, m2 into s square into y2 of s. So this is simply b2 into s into, okay, sorry, b2 into s into y2 of s. This is k2 into y2 of s plus m2 into s square into y of s. So this is your equation 4, right? Now what I want to find out is you somewhere or other you need an equation relating only y1 of s and f of s. Now coming to this expression, that is from the fourth expression, you will be able to get what? y2 of s from 4, right? From 4 you can express y2 of s in terms of y1 of s, right? Okay, so you can bring all the y1 of s terms to the other side, and you can find out what is y2 of s in terms of y1 of s from this equation, right? From the fourth equation. And substituting y2 of s, that term in terms of y1 of s in this equation 3, you will be getting total an equation relating f of s and y1 of s. Okay, I repeat, you can make use of equation 4 to find out y2 of s in terms of y1 of s. Now, coming to equation 3, you have y1 of s and y2 of s. Instead of y2 of s, you put this term in terms of y1 of s here, so that this equation becomes what? Total equation containing only y1 of s and f of s. And from that, you can very well find out the ratio y1 of s to f of s. So you may just do that by yourself and you will arrive at this result. Okay, now after doing as I said, you will be getting a very long answer. The numerator is m2 s square, m2 into s square plus b1 plus b2 into s plus k1 plus k2 divided by, and the whole these thing comes is a part of the denominator. So I'll just read it for you. It is m1 m2 s raised to 4 plus m1 b1 plus m1 b2 plus m2 b1 into s cube. So this is the coefficient of s cube, and the coefficient of s square is m1 k1 plus m1 k2 plus m2 k1 plus b1 b2 into s square, and the coefficient of s is b1 k2 plus b2 k1 into s plus k1 k2. Okay, so just check whether you're getting this answer. Okay,